Hello friends, hope you are all doing safe and healthy. Welcome to Vidyanmala. In this video, I wish to talk about an experiment on determination of total hardness of water. So, mostly in all my videos till today, I talked about the importance of chemistry, where I mentioned exactly what water is going to play a role in our life. I told you that we started our life with water and we will have definitely a sacred bath when we die. So, water is going to play a very important role in everyday life. So, Jalam Jivamrutam, water elixir of life. So, imagine on a hot sunny day, and when you didn't find a single drop of water to drink, how you feel. Even if you get that water, and if you find that water is not potable, it is not used to drink, how do you feel? Moreover, in chemical science, we called water as universal solvent, which means water dissolves everything in it. It is going to dissolve everything in it. Surprisingly, seawater contains all the elements that are known to us in the periodic table. Let's begin with the study for today's experiment. Then, how do we define hardness of water? Hardness of water is defined as the characteristic property of water which prevents the lathering of soap. So, what do you mean by the word characteristic property? It means unique. No other such substance will show such a property except water. No other substance will show such wonderful property. In the comment section, please mention what is your characteristic property. For me, my characteristic property is the way I teach, the way I exemplify different concepts. So try to write your characteristic properties in the comment box. I'll just go through. What is that property which prevents the lathering of soap? What is soap? Soap is chemically sodium or potassium salts of higher fatty acids. Soap is chemically sodium or potassium salt of higher fatty acid. For example, C17H35COONA, which is what we call as soap. So whenever you take soap and whenever you rub it with water, if it forms lather, the water is soft in nature. If the water does not lather readily, it is what we call as hard water. Then what is the reason for this particular property of not forming lather with soap? The reason is due to the presence of bivalent salts of calcium and magnesium. As I mentioned earlier, water, universal solvent, it dissolves everything in it. As and when water is flowing from its originating place to its estuarine point, it comes in contact with many soil textures. So, they dissolve calcium and magnesium salts into water. That calcium and magnesium salts will cause soap to form scum. Mostly in some of the textbooks it was written as precipitate, accepted, but technically it is called as scum. Whenever you rub water with soap or vice versa, it should form foam or lather readily. But due to the presence of calcium magnesium salts, it forms a scum. Such unique property is called as hardness. Except water, no other substance shows such a property. So, do you find any solution to remove hardness? Yes, based on the ions present in water, hardness can be classified into two types. One, temporary hardness, the other is permanent hardness. Temporary hardness is due to carbonates and bicarbonates of calcium and magnesium. Temporary hardness is due to carbonates and bicarbonates of calcium and magnesium. Whereas permanent hardness is due to chlorides and sulfates of calcium and magnesium. If you could observe this slide, what I did, temporary hardness I placed in green in color, permanent hardness I placed red in color, which means temporary hardness can be easily removed by just boiling or by Clark's process. Temporary hardness can be removed easily by just boiling or by Clark's process. In Clark's process, we add lime to water and the hardness causing substances will be precipitated. That precipitate we will remove and we will make the hard water into soft. But whereas in case of permanent hardness, you require some special treatments like zeolite process, ion exchange process, etc. So when these combinedly called, what combinedly called? Temporary hardness and permanent hardness combinedly called as total hardness of water. It is combinedly known as total hardness of water. It is very easy. You just take a glass of water, which you generally use. In that, add a small piece of soap. If the soap dissolves in water and forms a foam, the water is soft in nature. If that forms some scum like material, like precipitate like material, the water is hard in nature. What are responsible for a hardness? Chlorides, sulfates, permanent hardness, carbonates, bicarbonates of calcium and magnesium, temporary hardness. Then how do you determine total hardness? We determine total hardness by using EDTA. EDTA. And this determination is a experimental procedure. And we call it as complexometric titration. We call it as complexometric titration. What do you mean by the word complexo? What do you mean by the word metric? What do you mean by the word titration? Titration is the process of determining the concentration of a test sample. Here the test sample is water. To know the concentration by a process is known as titration. Then what is meant by metric? Which means measurement. Then what is complexo? Complex is a chemical species formed by the reaction between a metal and a ligand through coordinate covalent bond. Complex is a chemical species that is formed by the reaction between a metal and ligand through a chemical bond. So, in complexometric titrations, we will measure the formation of complex by titration. Complexometric titration, measurement of formation of complex by a titration, is what we call as complexometric titration. Then what is a ligand? In coordination chemistry, a ligand is a chemical species which is having one or more electron pairs with it. One or more electron pairs with it. For example, water. In water, oxygen possesses 2 electron pairs in it. In ammonia, nitrogen possesses 1 electron pair in it. So, water and ammonia are the examples of ligands. So, ligands, simply to make you understand, a person who is having money in large excess is a ligand, and that person will donate to other and forms a bond, and that is simply called as a complex. So the person who is donating money is a ligand, the person who is taking money is a metal, and there is a bond, and that bond is complex, and that bond is a coordinate covalent bond, and that entire species is called as a complex. And here we classify ligands as such, like neutral ligands which does not carry any charge like water and ammonia, negative ligands which carry a charge, minus charge, like fluoride, chloride, bromide, iodide and cyanide, and we have positive ligands, nitroso ligands. Moreover, based on the number of electron pair donating atoms, we can classify ligands as monodentate ligands, bidentate ligands, polydentate ligands. Monodentate ligands, which means one atom will donate electron pair. So the ligand is 1. Bidentate, there are 2 atoms which donates electron pairs. Polydentate, more than 2. For example, water molecule, ammonia, fluoride, all these are monodentate ligands. There is a wonderful compound called ethylene diamine. It is a bidentate ligand, and as I mentioned previously, EDTA, ethylene diamine tetraacetic acid, which is what we call as hexadentate ligand. Please observe the structure which is shown exactly bottom on right hand side. It is what we call as ethylene diamine tetraacetic acid. Ethylene at the center, CH2CH2, diamine, NN, exactly opposite, tetraacetic acid, 4 acetic acid molecules you have to place, CH2COOH, CH2COOH, CH2COOH and CH2COOH. Here 2 nitrogens, 4 oxygens will donate, which means 6 atoms will donate, and called as hexadentate ligand. Hexadentate ligand. And why I have chosen EDTA? We have water, we have ammonia, we have chloride, like we have many things, no? So why I have chosen EDTA? Because EDTA forms chelate complexes. CHELATE. EDTA forms chelate complexes. What do you mean by chelate complexes? See, mostly all chemical compounds have a particular shape and structure, like trigonal, linear, pyramidal, trigonal, bipyramidal, hexagonal, icosahedron. You find many structures. All these structures are somewhat stable and somewhat unstable. But if a chemical compound which is formed by a ring-like structure, if a chemical compound that is formed by a ring-like structure, they are highly stable. So EDTA, when reacts with a metal, it forms a ring-like structure. That's what we call as chelate structure. These chelate molecules are highly stable. These chelate molecules are highly stable. So to make a highly stable complex formation, I have chosen EDTA as my ligand. What is the other condition in this experiment? The other condition in this experiment is the stability of complexes is highly influenced by pH of the solution. The stability of the complex is highly influenced by pH of the solution. For doing experiments with EDTA, the pH of the solution must be maintained at 10. So to maintain the pH at a particular value, we have to use a very wonderful chemical compound called buffer solution. So here we will be using a basic buffer prepared by mixing ammonium chloride and ammonia. You may ask me, how do you mix these two? We have a wonderful equation called Anderson's equation. Using that equation, we will calculate the amounts and we will prepare the basic buffer. Then we will add the basic buffer to maintain the stability of the complex to more. So what we have to find out? We have to calculate the total hardness. How do you find out? By CMT. What do you mean by CMT? Complexometric titrations. What exactly we need to do this experiment? We need ligand. What is the ligand? EDTA. What are the metals? Calcium and magnesium. Do you agree? Yes, of course, because calcium and magnesium belong to the second group of elements called alkaline earth metals. So here calcium and magnesium, those two are metals. These two metals are present in water and water is colorless. Then come to EDTA. EDTA is a colorless substance. These two are colorless. The one which we take in the burette is colorless. The one which we take in the conical flask is colorless. Then what we are in need of? We are in need of a wonderful substance called eriochrome black tea. It is also known as solochrome black tea, eriochrome black tea or solochrome black tea, which is used as an indicator. And this indicator is blue in color as shown in this slide. This indicator is blue in color itself. It is blue in color. When this indicator is added to metal, it shows wine red color. When this indicator is added to a metal, it exhibits wine red in color. So what is the procedure to be followed? You have to take standard EDTA solution. You have to standardize the EDTA solution and then fill it in the burette. Take a clean conical flask and into the conical flask add the sample of water to be tested. then add pH 10 buffer, then aerochrome black tea. Immediately you get wine red color. You can see that there in the second diagram. And titrate by drop adding from the burette into the conical flask. You will find the change of color from wine red to pale blue. Okay. And then there is a very simple formula. Total hardness is equal to volume of EDTA rundown multiplied by normality of EDTA or concentration of EDTA into 100. Why we take 100 here? Because the GMW, gram molecular weight of calcium carbonate, is 100. According to some standard values, some standard rules of chemical science, express hardness in terms of CaCO3 only, because as its GMW is 100, it is very easy to calculate or multiply or division or computations. So multiplied by 100 multiplied by 1000, because we have to calculate in liters, no, divided by volume of water sample taken. So this is the formula by which you calculate the concentration of hardness that is present in the given solution. Always hardness is expressed in terms of ppm, parts per million, or milligrams per liter, mg per liter. 1 ppm is equal to 1 milligram per liter. 1 ppm is equal to 1 milligram per liter. There is a problem. I have taken 20 ml of sample of water and I got a standard EDTA solution 0.01 molar. So the titration value was about 12.3 ml. What will be the total hardness? Volume equal to 12.3, no, 12.3 into normality 0.01 molar into 100 into 1000 by 20. That is the answer you will get. Here in the same problem, the same sample of water is boiled and cooled, which means after boiling and cooling, temporary hardness removed. You will have only your permanent hardness. So 3.8 ml is for permanent hardness. So total hardness, you get some value. You get some value for permanent hardness. Total minus permanent, you will be getting for temporary hardness. So you may ask me a question, what after doing all this? You have standards for drinking water. Say according to BIS or IS standards, a sample of water to be potable when the hardness value lies in between 300 to 600. There must be 300 and it should not cross beyond 600. The same value for WHO also. I hope I'm clear. Thank you.